Robots in space.
Hello everyone, I'm Mike DiVerde and I'm an aerospace engineer. Today I'm wearing my Delta rocket shirt. On the left, you see a Delta IV Heavy liftoff, and on the right, the black cone is the type of payload adapter that I designed for 4-meter and 5-meter rockets 30 years ago. The silver cylinder is the mass and stiffness simulator that flew on the very first Delta IV Heavy flight. But hanging off the side of the silver simulator is a very interesting payload. I worked with the Air Force Research Lab to develop, fab, assemble, and fly in 30 days a support for their nanosat launch. On today's episode of Robots in Space, I will discuss research by Chinese scientists on a large solar energetic particle event and the impact of Mars measured by the Chinese Tianwen-1 Mars orbiter, along with data from 3 other spacecraft. The radiation environment at Mars is very harsh, and it is not well understood, which makes this research important. Tianwen-1 was China's first successful Mars mission, launched on July 23, 2020. The mission consisted of an orbiter, lander, and rover named Zhurong, making China the second nation after the United States to successfully land and operate a rover on Mars. The mission represented a significant achievement for Chinese space program and contributed valuable data about Mars geology, climate, and potential water ice deposits beneath the surface. The spacecraft reached Mars orbit in February 2021, and on May 14, 2021, the lander successfully touched down in Utopia Planitia, a large plain in Mars' northern hemisphere. The Zhurong rover, equipped with cameras, ground-penetrating radar, and instruments to analyze Mars climate and geology, operated on the surface for about 1 Earth year, far exceeding its planned 90-day mission. The rover entered dormancy in May 2022 due to declining temperatures and dust storms, and while attempts were made to reestablish contact, it has not responded since. The orbiter continues to function, conducting its own scientific observations of Mars and serving as a communications relay. The Mars Energetic Particle Analyzer, MIPA, was one of the scientific instruments aboard China's Tianwen-1 orbiter. It was designed to study energetic particles in Mars' space environment, particularly focusing on measuring solar energetic particles, SEPs, galactic cosmic rays, GCR, particles trapped in Mars' weak magnetic field, the interaction between solar wind and the Martian atmosphere. MIPA had the capability to detect ions with energies between about 50 kiloelectron volts to 12 megaelectron volts, and electrons from 50 kiloelectron volts to 6 megaelectron volts. The instrument helped contribute to our understanding of Mars' space weather environment and the planet's interaction with solar radiation. Let me break down the key differences between some of the solar phenomenon. Solar energetic particles, SEPs, are much higher energy particles compared to the solar wind. They can be accelerated by both solar flares and coronal mass ejections. Energies range from a few mega electron volts to giga electron volt levels. They can pose significant radiation hazards to spacecraft and astronauts. They occur intermittently, usually associated with solar events. Now, solar flares are sudden, intense bursts of radiation across the electromagnetic spectrum. So not particles, but radiation, photons of different frequencies. They primarily emit X-rays and extreme ultraviolet radiation. They can accelerate particles to create SEPs. They travel at the speed of light and reach Earth in about 8 minutes. They generally last minutes to hours, but they can disrupt radio communications on Earth's day side. Now, the solar wind is a constant stream of low energy charged particles, mostly protons and electrons, flowing from the sun. Typical speeds range from about 300 to 800 kilometers per second. They're always present, creating this continuous background flow in space. Shapes the heliosphere and interacts with planetary magnetic fields. Now, on the other hand, magnetic storms are large-scale disturbances in Earth's magnetic field. And they're usually caused by coronal mass ejections hitting Earth's magnetosphere. They can last for days, and this is where you've seen your aurora. The magnetic storms are what's behind your visible aurora at high latitudes. They can induce currents in power grids and pipelines. They affect satellite operations and navigation systems. They're not a direct solar phenomenon, but rather Earth's magnetic field response to solar activity. A key distinction to remember is that solar wind and magnetic storms are broader environmental phenomena, while solar flares and SEPs are more discrete events. They're all interconnected, though. For example, a solar flare might produce SEPs, which then interact with the solar wind and potentially trigger a magnetic storm at Earth. An astronaut traveling to Mars might encounter solar energetic particles, SEPs. They're produced by solar flares and coronal mass ejections. They're primarily consisting of protons and electrons. They're more intense but sporadic exposures, and they can deliver very high radiation doses during solar events. Here are the effects at different dose levels for acute exposures. So, in the range of 50 to 100 milligray, and milligray is your unit of radiation, right? Between 50 and 100 milligray, there's mild blood count changes that might be detectable. There's no immediate noticeable symptoms. There's slight increases in long-term cancer risks. But then you get to a zone of 500 to 1,000 milligray. Now you have the definition of this whole body exposure threshold for radiation sickness at 500 milligray. So that's the level that we're going to be very concerned about, right? Nausea and fatigue may occur. There's temporary changes in blood cell counts. There's much more significant increase in cancer risk, and there's usually no immediate severe effects. Now let's put these levels in perspective for a moment. For context, when you get a typical chest X-ray, you're getting about 1/10 of a milligray. Now, 1 milligray is actually defined by this. It's the average accumulated background radiation dose to an individual over a 1-year period as somebody who lives in the United States. So your typical American getting an average amount of radiation during a full year is going to get 1 milligray. Now, On the other hand, the astronauts on the International Space Station might receive between 50 and 100 milligray per year. So you see that they're getting like 100 times more radiation exposure in space. One thing to keep in mind as we go on to Mars is that even the astronauts on the space station have protection from Earth's magnetosphere, and Mars, they will not. Now we will discuss the primary research paper entitled The 2022 February 15 Solar Energetic Particle Event at Mars, a synergistic study combining multiple radiation detectors on the surface and in orbit of Mars with models. The research paper concludes that the February 15th, 2022 Solar Energetic Particle Event at Mars was significant in enhancing our understanding of Mars' radiation environment. The study combined data from multiple spacecraft to reconstruct the SEP energy spectrum and assess the radiation doses at Mars orbit and surface. They had data from multiple spacecraft, including the Chinese Tianwen-1, which provided high-energy proton flux measurements between 20 and 100 megaelectron volts, using the Mars Energetic Particle Analyzer, MEPA. The American MAVEN orbiter offered continuous low-energy SEP measurements below about 6 megaelectron volts. The European ExoMars Trace Gas Orbiter conducted orbital radiation dosimetry measurements using the Leolin MO dosimeter. The American Curiosity rover, one of my favorites, measured surface radiation using the Radiation Assessment Detector RAD. The second type of evidence for their conclusions includes the reconstruction of the SEP energy spectrum. The study reconstructed the SEP energy spectrum from 1 megaelectron volt to 1 gigaelectron volt by combining data from MAVEN, Tianwen-1, and Curiosity. The reconstructed spectrum was validated against dosimetry data from Trace Gas Orbiter and Curiosity. The third type of evidence for their conclusions is their radiation dose calculations. The calculated radiation doses at Mars orbit and surface were compared to the recorded doses, showing a discrepancy of less than 25%, which validates the reliability of the reconstructed spectra and measurements. The study emphasizes the necessity of continuous and synergistic radiation monitoring at Mars to better understand and mitigate the radiation hazards for future crewed missions. Overall, the study highlights the critical role of combining data from different spacecraft to provide a comprehensive assessment of the radiation environment at Mars, especially during large SEP events. Quoting from the paper now, there is a growing interest in exploring Mars in the coming decades. However, a significant obstacle that remains is the presence of space radiation, which poses a considerable and unavoidable threat to crew health, especially during long-term stays in future Martian habitats. Of particular concern are sporadic energetic particle events caused by strong solar eruptions, which can increase radiation levels in deep space and near Mars to potentially dangerous levels. Notably, a solar energetic particle event on 15 February 2022 has caused the first significant radiation enhancement at Mars in solar cycle 25, as observed by ESA's Trace Gas Orbiter, the Chinese Tianwen-1 orbiter, as well as NASA's Mars Atmosphere and Volatile Evolution spacecraft, and of course, the Curiosity rover. By combining data from measurement and modeling techniques, we reconstruct the energy spectrum of this SEP event to understand the potential radiation hazards at Mars. My summary is that the research paper did a good job in combining data from several spacecraft to assemble an overview of the radiation environment at Mars during one solar energetic particle event. The data highlights the radically different and harsh environment at Mars that humans, livestock, and plants would encounter on Mars compared to the very benign environment that we all enjoy here on Earth. On Earth, we are shielded by a huge and powerful magnetosphere, and we are safe. On Mars, there is no magnetosphere, and it is dangerous. Of note are the gaps in data that the paper points out. Even when using what is available from multiple spacecraft, the entire spectrum of radiation is not covered. Some instruments are pointed away from the sun and some towards the sun, and then some will vary in vector direction during the event. Each instrument has variable degree of shielding, either from the planet or the atmosphere or the spacecraft itself. Some instruments were overloaded by the intensity of the event, and valuable data was simply lost. The point is that there is not nearly enough instrumentation to determine what the radiation environment is at Mars. And that suite of instruments will need to collect data for a very long time first, because these powerful radiation events may occur sporadically and unpredictably. Only with this long baseline of quality data can the hazards be clearly understood. Without that deep understanding of this deadly environment, then it is not possible to provide a safe habitat on Mars for plants, livestock, or humans when they live there. Someday. OmniFuturists.
Robots in space.
Hello everyone, I'm Mike DiVerde and I'm an aerospace engineer. In today's superluminal episode of Robots in Space, we'll discuss the latest updates from the Perseverance rover on Mars and the latest weather reported by Curiosity at Gale Crater. Perseverance took this image on Sol 1396, which is January 23rd, 2025 for Earthlings. We'll spend a bit of time discussing this feature. The rock formations at the top of Hill 2 seem unusual. Kind of looks like a gigantic monster claw. Again, we look to Steve Alber's excellent map of the local area. The area that we zoomed up on is designated informally by Steve as Hill 2. And again, we look to Steve Alber's excellent panorama of the local area. The area that we zoomed up on is designated informally by Steve as Hill 2. Now we zoom up on Steve Alber's excellent panorama of the local area, and now you can see Hill 2 quite clearly, although it's still in the distance. Now that we've had a zoom out to take a look at the area that we're in, we're going to go back to the recent image from Perseverance of Hill 2 again. Now we have an extreme close-up on the intriguing features. This diagram shows some of the common features of an impact crater. I've highlighted the area that I think is relevant to the features that we see on Hill 2, impact melts. This diagram from the Lunar and Planetary Institute shows a cross-section schematic of a complex crater on the Moon, showing the locations of the different types of impact melts and impact breccias. Impact melt deposits can exist in a variety of structures and morphologies. Large kilometer-sized impact melt layers, kilometer to meter-sized isolated bodies within the crater interior and rim region, which is, I think, what we're focused on today, that type. There can be meter to centimeter sized glassy lenses and particles mixed within impact breccias in and outside of craters. There can be meters to centimeters thick impact melt dikes intruded into the crater floor, the central peak, and or the crater wall. And the last version is discrete centimeter to millimeter sized glass particles distributed hundreds to thousands of kilometers from the crater center. Lava on Earth is shown here for comparison. You can see similar structures as the monstrous fingers on Mars. This type of lava is a particularly sticky, viscous lava that flows in areas like Hawaii, as versus the explosions of sprays of ash that happen in other volcanic systems. Back to the Hill 2 image briefly to remind you of the shapes. Now I have added the blue curves that you see on the image here. I've added these curves to Hill 2 image to outline the shapes of the fingers. I want to emphasize them briefly for you to help you pick them back out again as we switch back to the original photo. Back to the Hill 2 image so that you have a chance to see the structures as they appear. My suggestion is that Perseverance has taken images of impact melts. I'm sure that there are other explanations for these structures. However, it is clear that it is an interesting specimen. Well, if there are impact melts, then where are the craters? Frankly, the evidence is very weak. I'm showing two copies of Steve Alber's excellent map that shows Hill 2. On the left, I'm adding a blue curve of the faint line of a possible crater. On the right, the same map without markings so that you can judge for yourself. Is it there or is it not? So we're on to my favorite section, the weather report from Gale Crater. Curiosity is taking daily weather measurements at Gale Crater in the southern hemisphere of Mars near the equator. At this location, it is currently middle autumn on Sol 4431, which is January 22nd for Earthlings. The high was 7 degrees Fahrenheit and the low was 101 degrees Fahrenheit. OmniFuturists.
Robots in space.
Hello everyone, I'm Mike DiVerde. I'm an aerospace engineer. Today I'm wearing my FA-18EF shirt. Super Hornet is a U.S. Navy supersonic fighter and attack aircraft. On the right photo, there's a label for the inlet duct. When I was a structural design engineer at Northrop, we designed, built, and flew the very first fiber-placed composite to ever fly. On today's episode of Robots in Space, I will discuss the NASA Messenger spacecraft, which investigated Mercury, and a recent research paper that hypothesizes the existence of a layer on that planet composed of diamond. Messenger stands for Mercury Surface Space Environment, Geochemistry, and Ranging. Messenger is a NASA-sponsored scientific investigation of the planet Mercury and the first space mission designed to orbit the planet closest to the Sun. The Messenger spacecraft launched on August 3, 2004, and inserted into orbit about Mercury on March 18, 2011. 7 years from launch to finally sliding into its orbit. After orbiting the planet for more than 4 years, the Messenger spacecraft impacted Mercury on April 30th, 2015. On the right is a true color image of Mercury, taken by Messenger. Note the quite dark color. This dark color is due to the abundant graphite, which is pure carbon. You know what else is pure carbon? Diamond. Here you see a diagram for the major spacecraft components and another for the scientific instruments. Note the sunshade, which is a ceramic cloth to help deflect the extreme environment near the sun. Earth is 93 million miles from the sun. Mercury is only 29 million miles from the sun at nearest approach. Also notice the X-band phased array antenna, which made its first appearance on a deep space voyage. We will also discuss the Mercury laser altimeter, the gamma ray spectrometer, and the neutron spectrometer next. NASA's Goddard Space Flight Center developed the Mercury laser altimeter, MLA. MLA mapped Mercury's landforms and other surface characteristics using an infrared laser transmitter and a receiver that measured the round-trip time of the individual laser pulses to determine the planet's topography. The data was also used to track the planet's slight forced libration, a wobble around its spin axis, which told researchers about the state of Mercury's core. MLA data combined with radio science Doppler ranging was used to map the planet's gravitational field. MLA viewed the planet from up to 1,500 kilometers, which is about 930 miles away, with an accuracy of 30 centimeters, about 1 foot. The laser's transmitter, operating at a wavelength of 1,064 nanometers, delivered 8 pulses per second. The receiver consisted of 4 sapphire lenses mounted on beryllium structures, a photon counting detector, a time interval unit, and processing electronics. Gamma ray and neutron spectrometer packages separate gamma ray and neutron spectrometers to collect complementary data on elements that form Mercury's crust. The gamma ray spectrometer measured gamma rays emitted by the nuclei of atoms on Mercury's surface that are struck by cosmic rays. Each element has a signature emission, and the instrument looked for geologically important elements such as hydrogen, magnesium, silicon, oxygen, iron, titanium, sodium, and calcium. It also detected naturally radioactive elements such as potassium, thorium, and uranium. The neutron spectrometer mapped variations in the fast, thermal, and epithermal neutrons Mercury's surface emits when struck by cosmic rays. Fast neutrons shoot directly into space. Others collide with neighboring atoms in the crust before escaping. If a neutron collides with a light atom like hydrogen, it loses energy and is detected as a slow or thermal neutron. Scientists looked at the ratio of thermal to epithermal, slightly faster neutrons, across Mercury's surface to estimate the amount of hydrogen possibly locked up in water molecules and other elements. Measurements from Messenger's MLA instrument during the spacecraft's greater than 4-year orbital mission have mapped the topography of Mercury's northern hemisphere in great detail. The view shown here on the left is an interpolated shaded relief map of these data. The lowest regions are shown in purple, and the highest regions are shown in red. The difference in elevation between the lowest and highest regions shown here is roughly 10 kilometers. Among the prominent features visible here are the smooth northern volcanic plains and the enigmatic northern rise. The low-lying craters near the North Pole host radar-bright materials thought to be water ice. Despite the short distance to the Sun, the axis of Mercury is not tilted enough to expose the interior of the craters at the poles, providing perpetual darkness and extreme cold. On the right is a true color image of Mercury, which is remarkably dark, which is interpreted as abundant graphite, which is pure carbon. Now we'll watch a brief video that shows the mapping of the Mercury laser altimeter, accompanied by Jason Geringer's new composition entitled Mercury. Enjoy. Here we see a false color set of images of Mercury that shows the surface composition. The MASCS instrument was designed to study both the exosphere and the surface of Mercury. To learn more about minerals and surface processes in Mercury, the Visual and Infrared Spectrometer, VIRS, portion of MASCS collected single tracks of spectral surface measurements since MESSENGER entered orbit. The track coverage is extensive enough that the spectral properties of both broad terrains and small distinct features such as pyroclastic vents and fresh craters can be studied. To accentuate the geological context of the spectral measurements, the MACS data have been overlain on the MDIS monochrome mosaic. Here we see the low reflectance material, LRM, ejected from craters. Quoting from the research paper entitled Mercury's Low Reflectance Material, Evidence for Graphite Flotation in a Magma Ocean, targeted low-altitude thermal neutron measurements for 3 LRM-rich regions confirmed an enhancement of 1 to 3 weight percentage carbon over the global abundance, supporting the hypothesis that the darkening agent in LRM is carbon. Though seemingly unlikely on a terrestrial planet's surface, particularly one so close to the Sun, 2 explanations for carbon on Mercury's surface have been proposed. The first suggests that carbon could be exogenic, delivered gradually by comets over Mercury's history. The second suggests an endogenic origin, that any carbon that did not partition into the core of the planet would crystallize as graphite and would have floated to the surface, creating a primordial graphite flotation crust. Here we see a section through the planet. Quoting from the research paper, it has been suggested that Mercury differentiated through a magma ocean stage in which substantial heat and melting of the planet took place. Van der Kayden and McCubbin showed that the low FeO, iron oxide, content and limited density range of Mercurian melts prohibits nearly all rock-forming minerals from forming a primary flotation crust on Mercury, with the exception of graphite. And here they refer to figure 5. Furthermore, Mercury's shallow mantle results in a limited pressure and temperature profile that does not span into the diamond's stability field. Graphite is therefore the stable phase of elemental carbon throughout the silicate portion of Mercury, which is a primary prerequisite to the existence of a graphite flotation crust. Now we will discuss the primary research paper entitled a diamond-bearing core mantle boundary on Mercury. So the themes of this research paper are, number one, carbon speciation in Mercury's interior. The study reevaluates the forms of carbon present in Mercury's interior, considering high-pressure temperature experiments, thermodynamic models, and recent geophysical models. 2. Magma ocean and core formation. The research investigates the conditions under which Mercury's magma ocean and core formed, focusing on the role of sulfur and carbon. 3. Graphite and diamond stability. The paper explores the stability of graphite and diamond in Mercury's magma ocean and core mantle boundary, CMB. 4. Core crystallization. The study examines the crystallization process of Mercury's core and the potential formation of a diamond layer at the CMB. 5. Geophysical models. The research uses updated geophysical models to reassess the pressure and temperature conditions at Mercury's CMB. So the conclusion that was made by the authors goes like this. The authors conclude that while it is statistically unlikely for diamond to have been stable in Mercury's magma ocean, the formation of a solid inner core could have led to the crystallization of diamond from the cooling molten core. This process may have resulted in the formation of a diamond layer at the core mantle boundary, which has likely grown thicker over time. The study suggests that Mercury's unique reduced conditions and carbon saturation in different reservoirs have contributed to this potential diamond layer. Quoting from the paper, abundant carbon was identified on Mercury by MESSENGER, which is interpreted as the remnant of a primordial graphite flotation crust, suggesting that the magma ocean and core were saturated in carbon. We reevaluate carbon speciation in Mercury's interior in light of the high-pressure temperature experiments, thermodynamic models, and the most recent geophysical models of the internal structure of the planet. The formation of a solid inner core caused diamond to crystallize from the cooling molten core and formation of a diamond layer, becoming thicker with time. So an obvious question is, how deep would you need to dig on Mercury to hit this diamond layer? For that answer, we will now discuss another research paper entitled Gravity Evidence for a Heterogeneous Crust of Mercury. The study of the internal structure of Mercury is fundamental for understanding the formation and evolution of the planet and of the entire solar system. Mercury is constituted by a very large iron-rich core with a radius of about 2,000 kilometers, a 400-kilometer thick mantle made of iron poor and magnesium-rich silicates, and a silicate crust with an average thickness of 35 kilometers. The core is divided into a solid inner core with a radius between 1,000 and 1,500 kilometers, while the outer core is made up of convecting liquid of iron sulfide, which is also responsible for the magnetic field. Therefore, the answer appears that one would need to dig through about 435 kilometers of rock just to get to the diamonds. That is 270 miles of digging straight down. And that's to get to a material that can be made here on Earth in a factory. So here's my summary. The researchers did an excellent job of taking the data from the MESSENGER spacecraft as it orbited Mercury, determined what the elements were that were on the surface, found an overabundance of graphite, and evaluated how that graphite could have come to be on the surface of Mercury. One of their conclusions was that the entire planet of Mercury had very high levels of carbon throughout, and under the certain pressure and temperature environment that is occurring in the core as the planet began to cool, some of that may have formed a diamond. Those diamonds may have floated upwards. Once they got to the solidifying mantle section, created a diamond layer several kilometers thick. The problem is that you have to dig down almost 300 miles through rock just to get to the diamonds. OmniFuturists.
Robots in space.
Hello, Ben. Thank you for giving us some of your time to talk about your chapter in the book. Ben, you're part of the OmniFuturists, and you've written a chapter for our book, Future Visions. I think that we should definitely start with you telling us all a little bit about yourself, please.
I'm the eldest son of a fourth generation family business. My brother asked me when we were young adults if he could take over the family business, and I was okay with that. I had been pursuing music as a degree in college. After college, I was in the military. I had auditioned to be in the Navy band, but my drum set chops weren't good enough. But my recruiter found me a position as a journalist, and I really got into broadcast journalism. I think that's kind of how I even ended up interacting with OmniFuturists, was because of like my copy editing background was a little bit what got me the interview into the Transhumanist Party. It was while I was in the military, when I had about a year left to go, that I was like, what's after this? And I had the thought that maybe we could suspend ahead on artificial technology and theoretically keep on living. So that's kind of what made me go into health school. Afterwards, I was first pursuing pre-med, and I was thinking, well, if I'm a surgeon, I could learn how to hook up the head to an otherwise artificial machine. But then went into pre-physician assistant studies, didn't make physician assistant school the first couple tries I had, but went instead with public health realm, a little more talking about like administrative roles within healthcare systems, working for a Department of Health and Human Services, that kind of thing. And then got that, did a little travel, finally ended up coming back to Madison in 2015. I've been here ever since. I currently work in drug quality control. Been doing that the last 2.5 years, and I feel like it's a pretty good spot for me to be living my life mission of keeping on living and of helping products and therapies get to market that help people keep on living.
That's excellent. Thank you. And maybe also you could tell us a little bit about the topics that you covered in your chapter.
I am the director of longevity outreach for the U.S. Transhumanist Party. I'm kind of trying to remember how I got into the OmniFuturists. I think we were interacting about various books that were interesting, and I was happy to start interacting more. And then with my proofreading, copy editing background, I did help with the first Future Visions that came out last year in that way. AI is not my area. I very much look to the rest of the people in this community to help me know what I need to know about it. I kind of look at the headlines, but I feel like if I'm going to dig into anything, I need to dig into the longevity science stuff more. And even that, I'm not digging in as much as I used to. I feel like it's more my job to make sure that people are learning about longevity science than to actually be the expert in longevity science. But I also think that I got to get practice writing. And when OmniFuturists and you offered me this chance to write a chapter for this year, I thought, well, it's as good a chance as any. My first thought of how to write this chapter was going to be to do it all in one fell swoop. I think I tried that on a Sunday and maybe another Sunday. And it's like, oh, this just isn't happening. But then I thought, I know how to interview people, and I know how to get the quotes that they have given me and tie them one to the next, to the next, to the next. And that's how you write a story. I first learned the technique in broadcast journalism through doing TV stories, but then same principle for newspaper stories. Just use the quotes, let them be your scaffolding. And through doing that for the chapter in this year's book, and through allowing myself just to riff a little bit, as I sometimes do in all of my journaling background that I have, managed to get the 6,000 words that we were going for.
I want to say that I think that yours was probably the easiest to read, very fluid, very liquid. I really liked it. And the further point is that I think that one common thread in all of our futurist interests in transhumanism and other things is super longevity. That seems to be one topic where we all seem to find common cause. But I've got a quick series of questions that I'm curious about it, other than what you wrote. So the first one is, do you think that the economic singularity is likely to occur in the next 10 years? If not, when, if ever? And you can say pass if you wish, because you already said, AI is not necessarily my thing, but it's good background.
So it was 2 weeks ago now that DeepSeek was announced to the world, if I'm remembering timing correctly, 2 weeks ago tomorrow.
Something like
and
that,
then
yeah.
It was in yesterday's Washington Post headline that Elon Musk's real motivations were released about automating the whole workforce. So I don't know, it's sure knocking on the door loud. We'll see what happens. I mean, I don't know the degree. I mean, there is some degree that Elon Musk is getting pushback. I don't know how sharp those teeth are on that pushback that he's receiving. I guess I kind of feel like our job is to, while we might be more concerned about some aspects of this administration and how it is doing things so far, to also help people see, you've been complaining about this job that you've had for the last 30 years. You sure you want to keep doing it? Let's just automate it. I mean, now granted, we need to come together to make sure that we don't have people starving because everybody's out of work and everybody's on the streets. So I would say we could be close. I a little bit thought of reaching out to my interviewees after the thing from Elon Musk in the Washington Post yesterday, but I was like, well, they'll find out in their various ways. I feel like it's hard to not kind of hear what's going on these days in the news unless you are actively avoiding it. So I look forward to conversations with various people that know about me writing this chapter, or other people just that I talk about with these topics of, we'll see, how fast do you think our jobs can be automated? And how do we ensure this is a good thing if and when it happens?
I formed the OmniFuturists in 2022, and I think we just generally thought we had about 10 years to plan how to react to it. And you're talking about the crux of the problem, meaning, sure, almost all of us really would prefer to not have to work. The question is then, how do you live? And that's the part that hasn't been even worked on seriously. And that's the critical problem, because as you're pointing out, it's not going to take 10 more years at the rate they're going. And there is no plan. So that's the kind of the focus of the economic singularity for the OmniFuturists, is not so much is it coming or exactly when it's coming. It's the question of how do we survive it? So the next question might be, how do you think you would define the onset of the economic singularity? What does that mean to you?
I might defer to Mike. You have that equation when there starts to be mass unemployment comparable to like the Great Depression. If we have 30% or something that we can attribute to automation taking the jobs, it's a little concerning about, someone needs to check me on my history, but when people started losing their jobs in the late 20s, early 30s, and then because they didn't have money to spend, then that was a vicious cycle of more unemployment because not as much money to go around. So if this starts to happen, how the government can keep money flowing through the system, maybe that's kind of what happened right as COVID was hitting the scene and there's like, just keep money in people's pockets. That's how we're going to get through this right now. And yes, with some inflation concerns at that same time. But for this being a long term, not just like the pandemic hit and then we figured it out, but we are able to automate all the work that there is. I don't know. And I don't know if we in the OmniFuturists have quite reached an understanding of how there could be more work or where there would be more work when the work that we are accustomed to knowing about is starting to get automated. Please ask your question one more time, just in case I have one more thought that would fit.
I asked, how would you define the onset of the economic singularity?
Yeah. I mean, with an announcement like in the Post, I'm curious what the response is and how that starts to show up in the news cycles more. And I think as people start to recognize its imminence, that itself is, if that's what people are thinking is coming, that's kind of onset in its own way.
I'm going to just respond to a couple of the things that you pointed out. In the Great Depression, unemployment reached about 25%. And so I've been using that as kind of like an example to people of, for about 10 years, the Great Depression dragged on, and that was very high levels of unemployment. And I don't want to react every time it goes from an unemployment of 4% to 5%. So what I selected as relatively arbitrary, but quite unusual levels was unemployment rate of 10%. And also look at the labor participation rate. Among men, it's about 68%. It's declined about 18% over the last 70 years. So very slowly. If it were to decline another 18% from 68 down to 50, so only half of the men of working age, let's say 25 to 55, if only half of them still had a job, that would be catastrophic. Those were my indicator levels, but I think you're talking about some of the things that would be indicators that it has come. You've got massive millions of people losing their job to automation. One of the things that we look at that's different than, say, usually when we talk about this, someone will say, well, when the tractors came, the horses didn't have a job. When we went off the farm, we started working in the factory. There's going to be something to do, Mike. And here's the difference that everyone seems to overlook. The tractor didn't have to think. The factory assembly line didn't have any capability of thinking. The 1970s, when the robot arms in Detroit started welding together cars, they couldn't think. They just did a very narrow set of jobs. And that's what's changing is if you have something like generative AI or agentic AI where the software can do some very simple planning and decision making. And now you mentioned Tesla, they've got some bots. The Chinese have some humanoid robots. If you were to marry that sort of thinking capability, a very basic reasoning capability with a dexterous, mobile, ambulating robot, that's a human. And some of the Chinese bots are claiming that they're like $12,000. Okay, I'm sorry, there's no human that's going to be able to compete with a robot that only costs $12,000 that doesn't have sick leave or vacation or benefits. And, so anyway, that's the crux of the problem. So the next question after that, my friend, is how do you think that humanity should deal with the economic singularity?
I didn't know that this would be my conclusion when I started writing the chapter, but maybe with 1,000 words to go or thereabouts, it was at that point at least becoming pretty clear to me that it's not a revolutionary new idea. It's just we as humans need to come together to help work through this time. I think with the thought that if we get through this time and if we do our best to engineer this next phase in human evolution the right way, it could be really good for all of us involved. If it goes sideways or negative on us, then kind of this whole experiment that has been civilization is for naught. So a little bit like we have to work through this together to ensure that not only has everything up until now been worth it, but the prospect of what could be with figuring out how to use this technology appropriately is, I don't want to say like nothing better. It's not like it'll be utopia. There will still be problems to resolve. I do like the term, can't remember who coined it, but protopia, about just constantly working to make things slightly better. It's just that right now we have a lot of change coming at us very quickly. And so we do really have to all be participating as best we can to help this situation become the right one for our next direction as a civilization.
It's very good how you were talking through this, and I tend to simplify it just for discussion purposes of, there's two main paths. One is cyberpunk and one is solar punk. Okay. And so the cyberpunk is Blade Runner, and the ultra wealthy keep all of the profits from all the bots. All the concentration of wealth goes right up to the top like it normally does. And the rest of us are barely surviving. And the other version is kind of a solar punk or Star Trek economy, where that wealth that's generated by agentic AI and by cognitive automation is then redistributed so that everybody on the entire planet is supported. And so I'm hoping, and this actually goes into the next question, which is, that solar punk version is advocated a lot by our friend David Wood, that there might be a path to superabundance. So the next question actually is, do you think that we will ever achieve superabundance?
Yes, I am optimistic that this is how things, if we make it through this window of all sorts of change, it's almost like, how could this not be? No. There are all these dystopian things about like, you're going to have just the wealth concentrate all to the top. Maybe I'll go this way. I do think all of us deep down are good people. Sometimes you got to dig more, but I think very deep down, we're all good people. And I will make another exception for like sociopaths that just like the chemicals within them just aren't right. But then it's like, well, you can't hold them to blame for that. But I feel like all of us are good people, more or less deep down. Also, this is more optimism. I think that if we are willing to discuss things with people with differing views in a friendly manner, ultimately, the truth is what will settle out. I think right now we're struggling with that, which is anything I could say would be less dramatic than how terrible it really is for us right now, that there is such division amongst us about just some beliefs that just on the surface just don't fit. I was thinking about this a couple of days ago with a friend of mine, that he and we are deep down, I know that we believe very, very, very similar things, but like being around him can be challenging sometimes, but it's just like because of how we manifest a similar belief structure, but on the surface. And I think that kind of goes for behaviors as well as for if you ultimately decide one thing versus another on an issue. It's sad that there are wedge issues out there, and that it kind of makes it that I don't like that we have to decide either or sometimes. I know there's like this whole, like you're at a negotiation table and you start really strong in your belief, and then the other party's going to counter, and you eventually come to something you can agree upon. It a little bit reminds me of that with our certain positions on issues, that if we could kind of compromise on both sides, we could find a path that's like, well, that side's not going to be, no one's going to be, I can't say no one's going to be 100% happy. The people on both sides are going to be unhappy about it, but in the middle, it's like, well, this is the best we could do about it. So I do maintain an optimism that if we can start working together and discussing through our issues, if we all can recognize each other as people with good intentions deep down, I feel like superabundance is the what makes sense as what would be the result of us all working together to make it to this next stage of our civilization.
Yeah, I'm going to agree with you that it is certainly possible that we get to superabundance. I think my concern is, as you watch the chaos in Washington, D.C., There might be a neo-reactionary thread to this that, as you go to more like illiberal democracies, you don't always get a very fair economic situation for everyone in the population. You and I are in America, and so we're tending to focus on how might America deal with this. I have hope that other countries around the world might have a stronger social safety net and a more redistributive outlook, and not allow a couple guys to have trillions of dollars and hundreds of millions starve to death. Right. I'm not so certain America is going to be able to do that until disaster has already wrought its disaster, the deaths and destruction. So, it's that's why I tend to focus on the idea that the economic singularity might be a transition period, a very, very painful transition period, until through that pain we learn we actually do have to share. I mean, something we're taught in kindergarten is lost when you start working for a lot of people. But the next question, my friend, is, are you concerned at all about the arrival of artificial superintelligence? Not just the kind you and I are talking about now, that somebody who can stack boxes at a warehouse, for example. We're talking about superintelligence being far smarter than all human intelligence combined. Does that concern you?
I hope that we can be looked at by something. We as humanity can be looked at by something that is artificial superintelligence, and it see that we are good to keep existing, that we would be good for sharing with other planets. I think I've kind of had this thought about like if there are ETs out there, and if they're looking at our planet and they're like, these guys are terrible, we're not going to let them into our universal community just yet. If that's the case, maybe they're like, well, they're not hurting anything yet, so we can let them keep existing. They're not a virus that should just be stomped out right now. Isn't it from Star Trek that they also say, like, once they've learned light speed or something, then that's when they're taken into the universal community? I forget how they had this figured. Anyway, so I hope that we as humanity can start proving ourselves to ourselves enough, and then to anything else that might come along, that yes, we are worthy for this universe, and we are worthy for existence. I think that a sufficiently sensitive artificial superintelligence would recognize the beauty that is within us. I just kind of got to hope that we have programmed these precursors to that artificial superintelligence in a way that it can recognize the good in us and help us to be better to each other and for the universe as a whole.
I love that perspective. Thank you. The final question for you, my friend, is, and I think I know the answer from other things you've discussed, what other topic is first and foremost on your mind? For example, space travel and colonization, or super longevity, perhaps, or crypto, or geopolitics, or quantum mechanics and quantum computers, et cetera. I mean, is there, besides, the economic singularity and that kind of like, how do we survive type of thing, is there something else that's first and foremost in your interest levels?
I think like clearly the super longevity piece. I did join the Transhumanist Party without thinking that I ever needed to leave planet Earth. We do have the whole, well, if there's an asteroid coming our way, it'd be good to have a backup plan or something. But I do not feel like there's any point to a universe in which everything that is conscious and sentient dies eventually. Like, there is no carried forward memory of anything. It's like in the movie The Hangover, like they had a crazy night, but they were on roofies, so they don't remember any of what they did. So any of those experiences were just kind of wasted. I feel like it's the same thing in a universe where where everything dies, and on our planet now, where everything does indeed die, unless you want to say like um, bacteria that replicate and split, and then that any of them that are here now are from the original and are inherently the original bacteria. But I feel like us keeping on living is what can give life meaning. If I could keep living this very life that I am right now and just keep living it, nothing got any more modern, I guess theoretically I'd be okay with that. I'd want to keep experiencing more of the world. But to me, that the possibility of keeping on living gives my existence meaning, and I would think everybody's existence meaning. There is this thought of like the terror management theory that the fact that we all die is what makes humans do all that they do, because they have this lingering thought in their head that at some point this is all gone. So I'm curious how humans will evolve, and once, fingers crossed, once we have this curing aging thing figured out, I'm optimistic for our future. I guess I feel like if we don't ever figure out this aging piece, there might not be a point to the universe and living anyway.
Very good. Thank you for your time. Everybody, you've got to read Ben's chapter. Now, our book, I think I've got this. Yeah, okay. This book is last year's book. It's already on Amazon. This book is the new one that's going to come out. It should be out by the time this video shows, but Ben's got an excellent chapter in Future Visions. It'll be available very soon. Ben, thank you so much for your time, your effort, your energy on all of these very important topics. Thank you for your time today, my friend.
Thank you, Mike. Appreciate it.
OmniFuturists.
Robots in space.
Jacob, welcome here. You're a great member of the OmniFuturists. You've written a chapter for our next book. Let's see if I can get the right one. Yeah, okay. This is this year's book, Future Visions. This one is last year's book. Let's start by having you talk a little bit about yourself. Tell everybody who's listening about Jacob for a little while, okay?
Well, I live in rural Kansas, and my interests include gardening and geology. I'm very interested in how we manage our resources to make civilization function and grow. Very early, I enjoyed entering essay contests when I was in high school, writing about things like water conservation and soil, due to my exposure to agriculture and realizing these things were the foundation of civilization early on. And that's part of why I wrote my chapter about the prospective technologies that could allow us to manage an energy addition for the economic singularity, because consuming more energy is a compounded endeavor, and we need sources of energy that work on new physical properties, in this case, the nuclear force, to supply the amount of energy that this is going to take. And the two main ways of getting that energy that I cover are small modular nuclear reactors of the next generation and deep geothermal power, which harnesses the decaying isotopes inside the Earth.
That's fascinating. Go back for a minute. I happen to know that you grow a bit of your own crops. Why don't you tell people about what you actually grow yourself?
Well, I live on my great-grandfather's old homestead that he came out here a long time ago. In fact, farming is one of the reasons why he wasn't allowed to march off to the Second World War, for food production. And I grow, I really like to grow squash, summer squash in particular. Asparagus patch. There's an orchard around here. Sweet corn's always good. I've got plenty of space. Potatoes are a reliable staple. I grow lots of those and store them so that I have enough to eat throughout the year. Um, but yeah, I like to grow and experiment with just about everything.
Excellent hands-on experience. You're not just talking about theoretics. You do quite a bit of this.
I've even lightly experimented with plant breeding.
Fantastic. Very good. Well, thanks for that beautiful introduction. And somehow I've lost visual on my questions. So hold on a second. Okay. So the first question, of course, is do you think that the economic singularity is likely to occur in the next 10 years? If not, when, if ever?
I believe we have achieved critical mass of tools, building better tools and harnessing energy more effectively. And I think is what bears that out now is you're seeing more and more of these corporate statements of how they're radically downsizing. You think about a big publicly traded oil company like Chevron today announced they're cutting 20% of the workforce. Gone. And that all comes down to these companies have access to technology that's better, faster, cheaper. And it exists. It's just a matter of rolling it out. And I think during the rollout, your people who have like lots of skills and seniority within these organizations will stay on for the rollout. But your people who are maybe just starting a career are going to have problems.
Oh, I would agree. And I'm going to add on a little bit that I think will lead you on to some of your favorite topics. One of the other indicators that you're getting close to the economic singularity. When I was a kid, we had 3 Mile Island and interest in nuclear died for decades. I mean, when was that? Late 70s, early 80s when 3 Mile Island hit?
Early 70s, I believe.
Early 70s. Okay. It's so far back I have trouble remembering. But here's the point: is there was a pun intended, a nuclear winter in nuclear power, and you look now at folks kind of openly talking about instituting one of your topics there, the modular nuclear reactors to power artificial intelligence.
Data centers.
That's not a minor consideration, considering how abhorrent many people thought nuclear power was for a long time.
Well, I thought we were going in a good direction when I first heard that the site that 3 Mile Island happened on is being recommissioned. I think that goes a long ways towards helping public perceptions around this that, wait, it's not a wasteland that you can never visit again. You can actually operate it again. And that maybe we went too far by scrapping this world leading nuclear program we had at the time. The reason
so let's go on to the next question is, how would you define the onset of the economic singularity?
I would define that as the point at which our ability to produce the things useful for civilization and transmute energy into the things useful for civilization, labor is no longer a limitation on the rate at which you can do that.
That's an interesting point on that. Yeah, I'm going to have to think a little bit about that. That's a good insight. How do you think that humanity should deal with the economic singularity?
Well, it's the age-old problem of learning to share resources. Because at present, there's a lot of natural capital that our system just allows people to collect rents on. And I believe to have a fair society, you have to invest everybody in that natural capital. And a small version of this that's already happened is like the Alaska Permanent Fund, where it's their oil being extracted, and every citizen in that state receives a piece in exchange for that extraction. And industry's happy because they make value-added products and they make money. And citizens are happy because their resource wealth is being shared with them.
Very good. The next one is, do you think that we'll ever achieve superabundance?
I believe we will because the mathematical constraint on how big an economy can get is how much energy is available to it. And between the geological and cosmic forces available to us, and just the multiple paths, superabundance is more than possible.
I'm going to
I
say
think
that
it'll.
your selection of nuclear energy as something you want to focus on is absolutely key, because we all know that if you were to stay with, say, coal or oil or natural gas,
uh,
and you do that exponential curve upwards in energy use that
You'll
might
drink the
occur.
entire milkshake. You'll just drink it all and not have it.
That reminds me of quite a scene in one of the movies. Let's see, was it Getty? Anyway, he was talking about
Oh,
how
there
he
will
would,
be blood. Yes,
there
Daniel
will be
Day-Lewis is
blood. He's got
great
the
in that.
long straw into
That's
your,
my favorite movie, in the bowling alley.
as soon as you said milkshake, that's what I thought of right away. Okay. Um,
Yeah, and this goes back to something we've been dealing with for a long time. That in 1956, Marion King Hubbard, one of the early founders of Technocracy Inc., wrote a paper about his Hubbard peak theory and how he was modeling the supply of hydrocarbon fuel in the world and how you would gradually produce more and more and more and you'd peak. And he did similar peaks for high grade, low sulfur coal and such. And his basic fact was he figured conventional reserves in the United States would top out in about late 60s, early 70s, and about 1970, that peak hit and production declined because conventional was topped out. The shale revolution has given us a reprieve, and recovery factors in shale are pretty low, so that buys us a lot of time to figure something out.
no, that makes sense. As long as we're talking about fission, how do you feel about the future of fusion?
I like fusion a lot.
Very
Fusion is
good.
the path to becoming a type 1 civilization.
I like it. I thought that might appeal to you. Okay.
I I think a society that has nuclear fusion probably has a cultural renaissance from all the bandwidth that people have freed up.
Okay. Very good. And are you concerned at all about the arrival of superintelligence?
Well, I'm not because it's inevitable, and we already have technologies that I'd be way more concerned about. Like if they didn't exist and you told me they were coming, like if I didn't know what a nuclear weapon was and you explained what this is and how like a bunch of the world's governments are going to have these laying around, that would terrify me. But we seem to have had restraint as to not destroy ourselves with them. So yeah, super intelligence scares me way less than, say, a nuclear weapon.
I think that superintelligence might be a key towards superabundance, is that they this higher intelligence may be able to reason out a plan to control this cognitive automation, all the bots and AI, to orchestrate
Well, and
factory
there's
developments and production to the point at which we achieve
and there's
superabundance.
also types of scientific research I flat think you need some kind of a synthetic mind to do because human scientists, we have all kinds of models and things that we interpret the world through, but there's some things that an artificial intelligence would be better at understanding just from being able to grasp and integrate a large number of facts.
I agree. I think you and I might think that the same sort of thing might happen with, let's say, plant breeding is one aspect, but genetic modification to, really, yeah, I know a lot of folks have a bad reaction to that term, but, to get really beneficial crops that grow in maybe parched areas, for example,
Mm-hmm.
or salty areas, for example,
Yes,
there's some
there's salt
benefits.
tolerant rice.
See, there's, and I think some of the GMO development of, as you point out, rice that has a bit more protein in it.
More vitamin A.
See, there's aspects that we're already seeing some use of machine intelligence to develop medications, but there's all kinds of other combinatorial solutions that you're pointing out your human brain is going to be limited on. Good points.
Yeah, plant breeding has a lot of positive possibilities in itself as far
Yes.
as nature hasn't made any organism specifically for, say, producing biofuel with, but that's something we might do.
I recall some investigations into algae, I believe, for types of
Algae.
biofuel. Yeah. So out of all of that, then, what other topic is first and foremost in your mind? For example, space travel and colonization, or super longevity, or crypto, or geopolitics, or quantum mechanics and quantum computers. Do you have an esoteric topic that you just love?
Well, the cultural consequences of super longevity and super abundance, I think, are going to be profound. And I think I think life takes on a more of a significance when this fragility of this short, limited human life has been transcended and a person isn't putting the majority of their bandwidth into making a living. I think it'll be interesting to watch how we branch out the things we value, the activities we enjoy, because that's the thing is a lot of people never like really pick up hobbies because they're so busy just running and trying to catch a breath. And also, I think we'll be more responsible stewards of resources once we have longer time horizons.
I like
And
these
this is
perspectives. Very good.
and this ties back into the world of energy in the sense that when you get into things like nuclear power, that has a long time horizon and it takes a long time to amortize. And that's a lot of why nuclear power is not more common, is because capital is optimizing for shorter time frames. And there's other ways to get your money back sooner than building a nuclear power plant.
You know, on that particular topic, real quick, is there a reason why you like the modular and smaller nuclear power as versus what I'm used to, which is the colossal 20-year development of a multi-billion-dollar plant?
Well, if our institutions were in shape for it, I would not be at all opposed to an American equivalent of like the Mesmer plan, where they figure out a reactor design that works and just copy them everywhere. And we kind of had that in the 50s, although we didn't do it as uniformly as the French, but we did have public support for nuclear and the Dwight Eisenhower's peaceful atom speech and nuclear power even back then was thought of as the path to this post-scarcity world in the imaginations of the futurist of the time. But the small modular reactors have safety benefits to help with some of the fear around that. And also, I just think with America being a very market-oriented society, having a collection of competitors building these reactors and marketing them will be, you'll see better rollout. And these companies are trying to build very plug and play solutions to get over the fact that when you offer to sell somebody nuclear power, obviously the first thought is that sounds complicated and dangerous. So I think it's very nice that you have these companies trying to sell these like full service packages of we'll build the reactor, we'll sell you the reactor, we'll operate it and maintain it, plug and play. And that's what the data centers need right now.
That's an excellent insight. Everybody, Jacob has written an excellent chapter on how to power our future. Jacob, thank you for your time, for your energy, your efforts in writing this chapter for us. Have a great day, man.
Thank you. Have a good one.
OmniFuturists.
Robots in
Happy Pi Day, everyone. I'm Mike DiVerde, and I'm an aerospace engineer. Today, I'm wearing my Fighting Illini shirt and sipping my coffee from my Fighting Illini cup. Behind me, you see my beautiful wife and I on campus last year on our way to observe the total eclipse. Today's episode of Robots in Space, we will discuss the Illinois mission by the University of Illinois to develop techniques of fabricating and assembling composite structures in space by robots for the DARPA NOMAD program. Their experiment will fly up to the International Space Station on the Antares rocket and Cygnus robot spacecraft to demonstrate the viability of their technique. Cygnus is an expendable American robot cargo spacecraft designed for International Space Station resupply missions. It was initially developed by Orbital Sciences Corporation with financial support from NASA under the Commercial Orbital Transportation Services program. To create Cygnus, Orbital paired a pressurized cargo module, largely based on the multi-purpose logistics module, built by Thales Alenia Space and previously used by the Space Shuttle for ISS resupply. And then they combined that with a service module based on Orbital's Geostar, a satellite bus. Cygnus is typically launched using its parent company's Antares rocket from the Wallops flight facility in Virginia. However, it is able to fly on other launch vehicles. After the failure of an Antares rocket destroyed Cygnus CRS Flight 3 and damaged the Wallops facility, 2 Cygnus missions were launched with United Launch Alliance Atlas V rockets in 2015 and 2016. Additionally, 2 Cygnus missions have been launched on the SpaceX Falcon 9 rocket in 2024, with one more scheduled to launch in 2025. Now we'll watch a short video of a portion of the Cygnus robot spacecraft being handled in the factory. After that, we'll watch the launch of an Antares rocket with a Cygnus robot spacecraft headed to resupply the International Space Station.
T-minus 10, 5, 4, 3, 2, 1. We have engine start. Lift off Antares, NG-13 mission for Wallops Flight Facility. Engines at 100%. Attitude nominal. TVC's nominal. Core pressures are nominal. Engine chamber pressures are nominal. Attitude nominal. Power subsystem nominal. Altitude 10,000 feet. Attitude nominal. Core system performance nominal. Engine and TVC systems nominal. Velocity 1,100 feet per second. Attitude continues nominal. Max Q, attitude nominal. Power subsystem continues nominal. Altitude, 50K feet. Engine steady, 100%. Core VNG3 activated. MECO slew maneuver initiated. Attitude nominal. Engines at 55% and nominal. (14,000 feet per second). Main engine cutoff.
Main engine cutoff confirmed. Standing by for stage 1 separation.
Upper ACS enabled. Stage 1 SEP.
Stage 1 separation confirmed. The next milestone is fairing separation, which will come in about 40 seconds.
Altitude 100 kilometers. Roughly 15 seconds to stage 2 ignition.
Fairing separation confirmed.
Fairing separation.
4 minutes into flight.
Interstage separation.
Interstage separation confirmed.
Attitude nominal. Stage 2 ignition.
And stage 2 ignition is confirmed. Stage 2 is that solid rocket fuel that will burn for about 3 minutes and 43 seconds. Burnout will come about 7 minutes and 9 seconds into flight.
Stage 2 will burn for roughly 2 more minutes. Power subsystem nominal. Stage 2 attitude nominal.
Even something as common as a flame acts differently in space. We will watch 3 different videos on this. The nature of exothermic reactions and microgravity bears on the point of today's episode: fabrication and construction of infrastructure in space by robots.
Strange Flames on the International Space Station. Presented by Science at NASA. Fire, it is often said, is mankind's oldest chemistry experiment. For thousands of years, people have been mixing the oxygen-rich air of Earth with an almost endless variety of fuels to produce hot, luminous flame. There's an arc of learning about combustion that stretches from the earliest campfires of primitive humans to the most advanced automobiles racing down the superhighways of the 21st century. Engineers study burning to produce better internal combustion engines. Chemists peer into flames looking for exotic reactions. Chefs experiment with fire to cook better food. You would think there's not much more to learn. Dr. Foreman A. Williams, a professor of physics at the University of California, San Diego, would disagree. When it comes to fire, he says, we're just getting started. Flames are hard to understand because they're complicated. In an ordinary candle flame, thousands of chemical reactions take place. Hydrocarbon molecules from the wick are vaporized and cracked apart by heat. They combine with oxygen to produce light, heat, carbon dioxide, and water. Some of the hydrocarbon fragments form ring-shaped molecules called polycyclic aromatic hydrocarbons, and eventually, soot. Soot particles can themselves burn or simply drift away as smoke. The familiar teardrop shape of the flame is an effect caused by gravity. Hot air rises and draws fresh, cool air behind it. This is called buoyancy and is what makes the flame shoot up and flicker. But what happens when you light a candle, say, on the International Space Station? In microgravity, flames burn differently. They form little spheres, says Williams. Space station flame balls turn out to be wonderful mini-labs for combustion research. Unlike flames on Earth, which expand greedily when they need more fuel, flame balls let the oxygen come to them. Oxygen and fuel combine in a narrow zone at the surface of the sphere, not hither and yon throughout the flame. It's a much simpler system. Recently, Williams and colleagues were doing a space station experiment called FLEX to learn how to put out fires in microgravity when they came across something odd. Small droplets of heptane were burning inside the FLEX combustion chamber. As planned, the flames went out. But unexpectedly, the droplets of fuel continued burning. That's right, burning without flames, says Williams. At first, we didn't believe it ourselves. In fact, Williams believes the flames are there, just too faint to see. These are cool flames, he explains. Ordinary visible fire burns at a high temperature between 2200 and 3100 degrees Fahrenheit. Heptane flame balls on the space station started out in this hot fire regime. But as the flame balls cooled and began to go out, a different kind of burning took over. Cool flames burn at the relatively low temperature of 400 to 1000 degrees Fahrenheit, says Williams. And their chemistry is completely different. Normal flames produce soot, carbon dioxide, and water. Cool flames produce carbon monoxide and formaldehyde. Similar cool flames have been produced on Earth, but they flicker out almost immediately. On the space station, however, cool flames can burn for nearly a minute. There are practical implications of these results, notes Williams. For instance, they could lead to cleaner auto ignitions. One of the ideas that auto companies have worked on for years is HCCI, short for homogeneous charge compression ignition. In the automobile cylinder, instead of a spark, there would be a gentler, less polluting combustion process throughout the chamber. The chemistry of HCCI involves cool flame chemistry, says Williams. The extra control we get from steady-state burning on the space station will give us more accurate chemistry values for this type of research. Just getting started, indeed. For more information about strange flames and other mysteries in Earth orbit, stay tuned to science.nasa.gov.
Quoting from the research paper entitled Robotic Assembly of Truss Structures for Space Systems and Future Research Plans. On-orbit assembly of space structures introduce many advantages. These include inherent serviceability, inherent expandability, launch packing efficiency, ability to launch small units independently, incremental system upgrades, structural efficiency, aerial densities of 15 kilograms per meter squared for conventional hardware, essentially no increase in complexity with size, and the ability to build very large structures, for example, larger than 100 meters. The disadvantage of on-orbit assembly lies in the support system required to perform the assembly. However, the system is inherently reusable. That is, it can be applied to the construction of several components and does not increase in complexity with increasing structural size. In addition, the support system directly supports operational maintenance and repair. Once a structural concept has been defined, the actual assembly is a well-defined repetitive operation ideally suited to robotic techniques.
Think of this high-tech tinker toy as a giant recycling effort, literally. Engineers at NASA's Langley Research Center recently dug the pieces out of 6 crates that were in storage. The struts and nodes were from a research project done back in the early 90s.
You want to put it in like this?
The 315 struts and 84 nodes are part of a space structure concept for a large orbiting telescope, almost 46 feet in diameter. The idea was to design a lightweight and compactly stored configuration that astronauts could easily put together during a spacewalk.
The structure we have behind me was called the Precision Segmented Reflector. It's a 14-meter diameter. It's the primary support truss for the mirrors for the primary mirror of a telescope.
What was once a project for humans will now become an experiment for robots. Langley Human Robotics Systems researchers are working with the Goddard Space Flight Center and a university to see if machines can build the truss system.
West Virginia University and Goddard are starting to do research in robotic assembly and robotic operations in space. They have a huge facility. It's beautiful. It's new. They've got a big flat floor with a shuttle arm. They've got 3 or 4 other robots. So we decided it would be very nice to ship them this hardware.
But first, the humans used Langley's airplane hangar, the only place with enough empty available space indoors, to assemble the massive structure. That way they could ensure their robot colleagues stayed away would have all the pieces they need to try to put the puzzle together.
DARPA is entering the final phase of its novel orbital and moon manufacturing, materials, and mass-efficient design, NOMAD, program. After checking the feasibility of proposals in laboratory experiments, it is now authorizing small-scale orbital demonstrations. The NOMAD program was established in 2022 to focus on expedient completion of space infrastructure. To do this, the DARPA team behind the program championed the delivery of lightweight raw materials to space where they could be robotically fabbed and assembled in orbit. Illinois researchers are about to start a new phase of Mission Illinois, a study that will send a composite tube manufacturing machine to the International Space Station to produce new materials for space construction. NOMAD aims to test new materials that DARPA and the University of Illinois have developed, which might significantly enhance the near-future robotic in-space assembly process. Quote, "The material curing process we are using is well tested and understood here on Earth, and the challenge will be to see if we can manufacture it on orbit, in microgravity, radiation, vacuum, and all of the complex conditions in the space environment," unquote, Professor Sama Tawfik said. The team has 18 months to complete this mission, with the last 6 months being dedicated to sending the apparatus into space, connecting it to a small module outside of the International Space Station, and then having astronauts perform the experiments. Quote, "This will be the first demonstration of manufacturing in space," end quote, Tawfik said. Quote, "Realizing such structures will enable the next stage in humanity's space utilization and a future beyond our imagination." Reactive extrusion, when applied to carbon fiber reinforced plastic, refers to a manufacturing process where the polymer resin used to bind the carbon fibers undergoes a chemical reaction during the extrusion process, essentially curing the composite in situ while it is being shaped, allowing for faster production and potentially improved mechanical properties compared to traditional curing methods. This is often achieved by utilizing a reactive resin system that polymerizes rapidly upon mixing with a catalyst or initiator within the extruder. Quoting from the research paper entitled "Reactive Extrusion of Frontally Polymerizing Continuous Carbon Fiber Reinforced Polymer Composites." The manufacturing of carbon fiber reinforced polymer composites demands rapid and energy-efficient strategies. Frontal polymerization enables the manufacturing of carbon fiber reinforced polymer using dicyclopentadiene thermoset polymer, which meets these requirements. In this work, we introduce reactive extrusion of carbon fiber reinforced polymer, where two rollers provide localized heat and pressure to sustain the curing reaction and the consolidation of a continuous carbon fiber tow pre-impregnated with dicyclopentadiene. We studied the effect of the extrusion speed, temperature, and compaction force on the properties of the produced carbon fiber reinforced polymer. Mechanical testing confirms that the resulting fiber volume fraction and the elastic modulus are similar to bulk cured tows. A homogenized thermochemical model is developed to study the effects of the process parameters on the polymerization reaction. The process produces hollow woven composite tubes directly via extrusion and in situ curing. Overall, this process offers advantages in curing, tooling, speed, and energy. Quoting from the research paper again, compared to state-of-the-art continuous fiber thermoset composite additive manufacturing processes in published literature, the reactive extrusion carbon fiber reinforced plastic methods described in this paper compare favorably in terms of both printing speed and fiber volume fraction. The tow-based process maintains a printing speed that exceeds that of fiber placement-based direct ink writing of composite tows. Additionally, this process attains printing speeds and fiber volume fractions comparable to those of existing additive manufacturing processes of epoxy-based systems, but without the need for a post-cure in an oven. The reactive extrusion carbon fiber reinforced plastic process is therefore more efficient with respect to the total energy requirements for curing. This can be observed by the 4 orders of magnitude reduction in energy per unit volume for the RACFRP process compared to that of conventional curing in an autoclave. Simply amazing. So here is my summary. The Fighting Illini are leading the way to a space robot built of large, inexpensive, and energy-efficient fabrication and construction techniques anywhere in the solar system. They've already shown how to do it in the lab. Now they will soar on the Northrop Grumman Antares rocket and Cygnus robot spacecraft up to the International Space Station to see whether the reactive extrusion process works reliably in vacuum and microgravity. Microgravity produces some deviations in flame dynamics compared to Earth gravity conditions. We wait expectantly for their flight next year. OmniFuturists.